Hi everybody, here we go. We're going to do a little work in chapter 6, which is about a lot about vectors and then some work in polar coordinates also. So this is going to be a very fun chapter, but we got to start with some vocabulary. So we're going to start with vector. That's what this chapter is about. What is a vector? A vector is a directed line segment. A directed line segment. A vector has two qualities. It has direction, directed, has direction, and magnitude. It's a segment. Magnitude is a word farther down the list. Magnitude means length. Magnitude is the vector language for length. So because a vector is a segment, it has a defined length. And it also has direction. A position vector, vectors occur all over out here in space. So my arm is a vector, my leg is a vector. They're all vectors, they're all over the place. To kind of keep things standardized so that we can do math with these vectors, we have what we call position vectors, or vectors in standard position. And what that means is their vertex at the, or I shouldn't say vertex, I'll say their initial point, their starting point is the origin. So we can pick vectors up and move them, and we like to have them positioned at the origin. That is a position vector. It starts at the origin. Vector components. So let me just look at this vector I just drew, this position vector. This, make it a little bigger here. Here's my position vector. And we often put just one tip on there. It really doesn't matter. I don't want you to get all hung up about it. But 2 tips on it in geometry class indicated array. An array is very different from a vector. Array has direction, but array goes on indefinitely, and vectors do not, they stop. So to distinguish them from each other, we often put just one tip on it. I'm not gonna get all hung up about that, but you should know vectors and arrays are different, and therefore they should have different notation. Okay, anyway, here's my position vector, vertex at the origin. Now, if I were to drop my perpendicular, like I have done how many infinitely many times, this side is x and this side is y, and this side would be the length of the vector. This would be the length of the vector. So I'm going to indicate the length of a vector. I'm going to skip down here to magnitude. Magnitude is length. And the notation we use for that is absolute value. So when you put a vector inside what looks like absolute value marks, you're talking about its magnitude. So, got some angle theta here in standard position, and this right here is the magnitude of the vector. Okay? Now, I want you to think about something. First of all, x and y are the components of the vector. X and y are the components of the vector because x and y tell me how this vector moves. It's starting at the origin, it's ending here. So to get there, it goes this far horizontally and this far vertically. So the components of a vector are simply its x and y. And I want to show you something that we're going to use over and over and over again in some of our problems. If you go back to straight right triangle trigonometry that we learned a long time ago, would you agree that the cosine of theta is x over the magnitude? X over adjacent over hypotenuse, that's the cosine. And the sine is opposite over hypotenuse. So we would agree with that. No one's going to disagree with that statement. So if I am interested in the components of the vector, look at what x is going to end up equaling. If I multiply this over, doesn't x equal the magnitude times the cosine? And y equals the magnitude times the sine. So if I know the direction angle of my vector, this angle that it makes with the positive x-axis, standard position angle, if I know that angle, and I know my magnitude, then I can easily find the components using right triangle trigonometry. So x is always going to equal the magnitude times the cosine, and y is always going to equal the magnitude times the sine. Now, a little foreshadowing, and I'll probably lapse into it myself. If I think about a circle here, which again is not a foreign concept at all, the unit circle, that isn't the unit circle, but it's a circle. Instead of calling this the magnitude, I could call this r, the radius of the circle, which is exactly the same as the magnitude of the vector. But if I think of it as r, then x equals r cosine theta, and y equals r sine theta, where r is the radius of that circle, centered at the origin, going through this point. So r is the magnitude of the vector, and theta is the direction angle. Hang on to that thought because you're going to see that again, for sure. All right, so vector components are x and y. This is how we find it. Magnitude is length. Notation is the absolute value. The zero or the null vector is the vector whose components are 0, 0. Now, you're thinking to yourself, wait a minute. If the components of the vector are 0, 0, then that means that this vector moves over 0 and up 0. So in other words, it doesn't really move, and it's just that point right there. Well, I get that. I get why you're thinking that. But we have to have something that represents a vector that doesn't move. Because when you add two vectors, your answer has to be another vector. So we have to have a way of indicating, if we had opposite vectors, for example, we have to end up with another vector. And this is the vector we end up with, the null vector or the 0 vector. In a vector, the point where it starts is called the initial point. So if we're in standard position, if we have a position vector, our vector is starting at the origin, so the initial point is the origin. But it doesn't have to be. I could draw a vector out here somewhere. And this would be the initial point, and this would be the terminal point, starting, ending. Equivalent vectors are vectors that have the same direction and the same magnitude. So two vectors that have the same direction and the same magnitude are equivalent vectors. A scalar is just a real number. So like if we had the expression 3v, this obviously is a vector, vector v. We're timesing it by 3, and that is a scalar. So a scalar is simply a real number. So we have real number quantities, and we have vector quantities. And we'll talk about some more of that later. But a vector has direction and magnitude. A scalar is just a number. It's just a real number. The resultant of two vectors is this, or more, you can have a result of lots. A resultant is simply a sum, S-U-M, adding them. So we're going to add two vectors, and we're going to end up with another vector. We're going to add two vectors and end up with another vector. So an example, a quick example of that might be, you're familiar with how the room is. So I'm standing right here and I'm gonna get back to the desk in the back of the room. Well, in order to do that, I can't walk straight back there because we got furniture and people and everything else in the way. So if I'm gonna get back to my desk back there, I'm gonna have to walk this way first. So my motion, that's a vector. There I am, walking over here. Okay, then I'm gonna turn and I'm gonna walk back that way. So I'm gonna turn and I'm gonna walk back this way. And now I'm back at the desk. Now, that was two vectors. It was a vector for me straight ahead and then a vector turning right. That's what this is. But the net effect of all that moving around is right here. There is my resultant. So this was like vector U, my first vector. This was vector V, my second vector. But when I add those two motions together, the resulting magnitude and direction is that vector right there. It took me two vectors to do it, but if I could somehow, fly, that would be how I would fly back to my desk. Resultant, sum of two or more vectors. A unit vector is a vector whose magnitude is 1. A vector whose magnitude is 1. A unit vector, magnitude 1. Think about the unit circle. The unit circle is a circle centered at the origin with a radius of 1. Remember that? Lordy, I hope so. Unit circle is important. Every radius of this thing is a unit vector. Would you agree with that? Every radius I draw in there has a length or a magnitude of 1. Those are all unit vectors. Of all the unit vectors in the whole wide world, there are two that are the most important, and you can probably guess what they are. This blue vector right here, which has coordinates or components 1, 0, is called vector I. Now that is not I as an imaginary unit. I don't know why they called it I, Google it. That's I. Vector I has components 1, 0. It is called the horizontal unit vector. Obviously, the horizontal unit vector. This vector, the green one, is J, and it is components 0, 1, coordinate 0, 1, components 0, 1. It is the vertical unit vector. Every two-dimensional vector, so every vector we draw in the coordinate plane, can be written as a combination of I and J. It's very, very simple to do. Let me draw one. Let me say, let me come over 2 and up 3. So there is the vector whose coordinates are 2, 3. I went over 2 and up 3 when I drew it. Now, if I went over 2, then his horizontal components, 2 steps, 2 eyes. That's 2I. 2 horizontal units. And then 3 J's. 3 vertical units. So the vector 2, 3 can be written as the sum of 2 I's plus 3 J's. 2 I's means you're taking 2 horizontal steps, and 3 J's mean you're taking 3 vertical steps. And that would result in that vector right there, over 2 up 3. All right, and the direction angle of a vector? Well, here, let's look at my 2I plus 3J vector. This is called the direction angle. We'll call it theta. The direction angle is simply the angle in standard position. It is the angle that the vector makes with the positive x-axis. That is the direction angle of the vector. Obviously, every vector you draw is going to have a direction angle. And we'll be finding some of those here in a minute. It's real easy. All right, so let's do some problems now. We got some vocabulary under our belts. Maybe we'll run into some more as we do some problems, but let's check it out and see. Number 1 says, given these 2 points, 1, 3, and 2, negative 4, find vector AB. Now, I don't want you to make this hard, because this is pretty dang easy. Okay? Vector AB is the vector that moves from point A to point B. So I want you to think about how it is moving horizontally. If it is moving from where x is 1 to where x is 2, this vector is actually gaining 1 horizontal unit. Would you agree with me? It's moving 1 horizontal unit. So the x-coordinate of the vector is 1. 1 to 2. That's a difference of 1. In the y direction, it's going from 3 down to negative 4. So how many steps is it taking in the y direction if it's going from 3 down to negative 4? That would be negative 7. So the coordinates of this vector are 1, negative 7. In other words, in order to get from point A to point B, we go right 1 and down 7. That's it. Those are the coordinates of the vector. One thing I want you to notice is the coordinates of the vector are very, very similar to slope. Would you agree with me? If you look at these 2 points and I said find the slope, wouldn't the y change be negative 7 and the x change be 1? Those are the coordinates of the vector. Those are the coordinates. All right, now we've got a bunch of points. And we're doing something. We're going to determine if RS is equal to PQ. Now remember, if they're equal, they have the same magnitude, same direction. So in other words, they're going to have exactly the same coordinates. If 2 vectors are equivalent or if 2 vectors are equal, they're going to have exactly the same coordinates. So what are the coordinates of RS? We're going from negative 4 to negative 1. Watch your arithmetic. Negative 4 to negative 1 is a change of positive 3. And 2 to 6 is a change of positive 4. So those are the coordinates of RS. Now what about PQ? Order is really important, guys. You got to start at P and go to Q. So 2 to 5 is 3. And negative 1 to 3 is 4. Are these 2 vectors equivalent? Yes, they are, because they have exactly the same coordinates. They are moving exactly the same number of steps in exactly the same directions, right? 3 and up 4. All right, now we got a couple more points. Oh, no, we don't know one of them, so we don't know H. But we know that the coordinates of the vector are negative 3, 6. So in other words, if we drew a picture of this scenario, I'm starting at 3, 5. I have no idea where I'm ending, but I know in order to get, here's H over here, in order to get from C to H, I am moving this way. That's how I'm moving. My picture's not quite right, but you get the idea. I'm moving left 3 and up 6. That's how this vector moves. This is the directed distance of the vector. These are the coordinates of the vector. This tells me how it moves. So if I start at 3 and back up 3, then I'm ending at 0, aren't I? And if I start at 5 and go forward 6, or actually up 6, because that's y. If I start at 5 and go up 6, then I'm ending at 11. So the coordinates of the terminal point of this vector are 0, 11. Now we got the same thing. I'm just going to draw a picture of it. I don't know what R is. Don't know what R is. But I know S is 4, -3. And I know that RS, that is the vector that starts at R and goes to S, is 2, -4. So to go from R to S, I am going right 2 and down 4. So where did I start? So that if I went right 2, I ended at 4. Didn't I have to start at 2? Because if I start at 2 and go right 2, I end up at 4. Where do I have to start so that if I go down 4, I'll end up at -3? I don't have to start at 1, because if I start at 1 and go down 4, I'm going to end up at -3. Remember, the coordinates of the vector, when they say RS equals this, this is telling you how the vector changes. How does it move? It's moving right 2 and down 4. So where did you have to start? So that if you went right 2 and down 4, you ended up here. All right, number 5. Notice that number 5 is using the absolute value notation. And we talked about that a minute ago. We've got a couple of points, these are points. We're going to make a vector AB. So let's figure out what the coordinates of vector AB are. In other words, how does this vector move? How does it move? Well, we go from A to B. That's down, or left 2, we back up 2. And then we go from 2 to -4, so we're backing up 6. This vector moves back 2 and down 6. Now we want to know the magnitude of that vector. How long is it? Well, this is so easy, guys. So simple. Let's draw it as a position vector. It goes left 2 and down 6. So the vector would look like that. If I make my little right triangle, my butterfly bow tie, always, 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 -2, -6. That's how this vector moves. He goes left 2, down 6. This is his magnitude. What am I going to do to find the magnitude? I'm going to do the Pythagorean theorem. Absolutely. So that would be 2 squared, or 4, plus 36, the square root of that. A squared plus B squared, I'm looking for C. So that's 40, root 40, 2 root 10. Now, some of you are thinking, wait a second, Mrs. Ford. If I want to know the length of AB, could I just do the distance formula, our old distance formula, from A to B? And the answer is absolutely yes, you can. That distance is 5 minus 3 squared plus 2 minus 4 squared. Do you see that you're going to get the same thing? You absolutely are. And it doesn't matter how you do it. Be aware, however, that usually you don't know the original points. Usually all you know are the coordinates of the vector. So it's so easy to find the magnitude. If you have the coordinates of the vector, you simply square the first one, square the second one, add them up and take the square root. It's the Pythagorean theorem. Square the first one, square the second one, add them up and take the square root. And that will give you the magnitude every single time. Well, I hope so far you're loving your vectors, because all of it makes completely good sense. It's very logical. Let's see what happens now in number 6. Here are some vectors. I do not know where they are starting and ending. All I know is how they move. So these are the coordinates of the vectors. I got 3 of them. So here's how U moves. It goes left 1 up 3, right 4 up 7, nowhere sideways and straight up 6 is how W moves. Now I want to find the resultant of U and V. I want to add them together. Well, I wish you were here, because I hope at this point you would all be shouting, just add the X's and add the Y's, and you would be right. So the resultant is simply 3, 10. So if you think about it, vector U backs up 1, vector V goes forward 4. So isn't the net result of that forward 3? Vector U goes up 3, vector V goes up 7, so the net result of both of those is up 10. Easy peasy. 3U, here's our scalar multiplication. We're taking a scalar, a number, times a vector. And again, if you were sitting here, I know what you'd all say to me. Here's vector U, triple it. So -3, 9. Vector U backs up 1, so 3U's is going to back up 3. 4V minus W. Well, first of all, we got to do 4V. So 4V's would be 1628, 4V's. And then we're going to subtract W. So that's going to be 16 minus 0 and 28 minus 6. Easy. Now D adds a little twist to it. It starts out the same way. We are finding U plus 2V, the magnitude. So let's do U plus 2V first. So U plus 2V's will be 814. 2V's, double it, double V. Now I want to add those together, so that sum will be 717. So that is the resultant of U and 2V. Now I need the magnitude of that vector. So I told you a few minutes ago, you can draw this if you want, but when you draw it, you're going to go over 7 and up 17. So when you do your magnitude, when you do the Pythagorean theorem, you're just going to end up squaring 7, squaring 17, adding them together and taking the square root. So 49 plus 17 squared. So that's the square root of 338. And then I don't know if that breaks down. It does actually, because that is 2 times 169. So this is 13 root 2. 13 root 2. Okay? Easy enough. Now we're ready for E, right? E. Find a unit vector in the direction of U. Okay, so let's look at U first of all. Let's just look at U. U is the vector that goes left 1 and up 3. So here is a picture of U. It goes left 1 and up 3. There it is. There's a picture of it. It is not a unit vector, because a unit vector has a length of 1, and this is clearly not 1. What is this? What is the magnitude of vector U? Well, it's 1 squared plus 3 squared, square rooted, so it's root 10. The magnitude of that vector is root 10. I want the magnitude of that vector to be 1. I don't want to change the proportions of the sides. I don't want to change any angles. I just want to take that triangle and shrink it so that that is only 1. So to do that, I'm simply going to divide everything by the square root of 10. Because if I divide everything by the square root of 10, I haven't changed any proportions, I've just made it smaller. Now it's a unit vector. But now its coordinates are negative 1 over root 10, comma, 3 over root 10. Now its magnitude is 1. And that's how you make a unit vector. Okay, so basically, those of you out there who like to memorize stuff, how do you make a vector a unit vector? You divide its coordinates by its magnitude. Whatever the original magnitude was, divide your x and y by that, and you'll have yourself a unit vector. All right, here's vector v. We're supposed to write it, oh my, this sounds so fancy, write it as a linear combination of I and j. A linear combination of I and j. Now remember, I is simply one horizontal step. That's I. J is one vertical step. So, if these are the coordinates of the vector, then it is taking 4 horizontal steps and 7 vertical steps. That's all there is to it. That's all there is to it. So the problem sounds really, really hard. You can impress people when you say, I'm going to write this as a linear combination of I and j, but it's super simple. So u would be negative I plus 3j. I and j are simply horizontal and vertical units. So this is 4 horizontal units and 7 vertical units. Okay, number 7. Find the components, that's x and y, of the vector with a magnitude of 7 and a direction angle of 115. So, a direction angle of 115 puts us over here. Remember, we're measuring in standard position. The only time we don't measure in standard position is when we're doing navigation. You know that already. So there's 115. And the magnitude is 7. That means the length of that vector is 7. Now I am trying to find the x and the y. Before we had any conversation at all, before we started this video, you could do that problem. I hope. I hope what you would do is say, well, if that's 115, then this has got to be 65, because that's 180 there altogether. And if I want to find x, I can say something like cosine 65 equals x over 7. So x equals 7 cosine 65. And then I can do the same thing, only say sine 65 equals y over 7. So y equals 7 sine 65. So I can find the components, x and y. That's all you're looking for, x and y, by simply typing in 7 cosine 65, and I get 2.96, and 7 sine 65, I get 6.34. I need to make a quick check. I hope I'm in degrees here. Yeah, I am. Okay. All right. Now, there's something wrong with what I've done now. And this is my caution to you. If you choose to do the problem this way, you must pay attention to something. What is wrong with the coordinates? There's the vector. What is wrong with these coordinates? They're both positive. And if the coordinates are both positive, then your vector has to be in quadrant 1, and this one is not. This is in quadrant 2. So you need to manually adjust your x coordinate to be negative, because that's where you are. X is negative in the quadrant that you're in. Okay, so you know how to do that. Do it that way if you wish. There's nothing wrong doing it that way, but you must absolutely pay attention to where you are and make whatever adjustments you have to your SIGNs, because doing the problem this way, everything's going to come out positive all the time. So you're going to have to fix those negatives. My suggestion to you is you go back to what I reminded you of, or I didn't remind you, I told you and said, hey, hang on to this thought. It's going to be useful. In this chapter, there's a thought that's going to be useful a lot. And that thought is x equals r cosine theta and y equals r sine theta. X and y will always be found by doing r cosine and r sine. Because again, those are the definitions of cosine. Cosine is x over r. You memorize that. That's a definition of cosine. So cosine is x over r, so x is going to be r cosine theta. Well, in our problem, r, think of r as the radius of the circle, which is 7. So x is going to be 7 cosine theta, which is 115, and y is going to be 7 sine 115. See, if I do this, I don't need a picture. I don't need a reference angle. I don't need to worry about signs. Because when you type in 7 cosine 115, guess what? It comes out to be negative 2.96. And then 7 sine 115 is positive 6.34. So if you use the given magnitude and the given angle, you don't need a picture, you don't need a reference angle, you just type in r cosine and r sine, and that will give you your coordinates or your components. Those words are used interchangeably. So the components and the coordinates, component is the components are the horizontal and vertical parts of the vector, which is essentially x and y. Okay, number 8. Now here's where you really got to be paying attention to what's happening. So we got a plane flying on a bearing of 65 degrees. So remember, this is navigation. So 65 degrees looks like this. At 500 miles an hour. So the magnitude of that vector is 500. That's it. That's a picture of the situation. Now, if you're going to say you want x and you want y, x is going to be r cosine and y is going to be r sine. R is clearly 500. But theta must be in standard position. Navigational angles are not in standard position, so please don't use 65. Standard position would be this angle right here, wouldn't it? And how big is it? 25? So that is the angle you need to use. You must adjust navigational angles. So I know over here I was like, made a point that you don't need reference angles and all that. You don't, as long as your angle's in standard position, which is how it will always be, except for navigation. So when the angle is a navigational angle, you must translate it into standard position. Standard position means positive x-axis, starts at the positive x-axis. So that same angle is 25 degrees, and that would be the answer to the question. So the components of the velocity vector are 500 cosine 25, which is 453.15, comma, 500 sine 25, 211.31. Those are the components of the velocity vector. And what that means, in case you're thinking about, what does that even mean, Mrs. Ford? It means that if this airplane flies for an hour, 500 miles on that course, he will have flown 453 miles east and 211 miles north of where he started. Now, he didn't actually fly that far, but his end point is this far east and this far north of where he started. Hopefully that makes some kind of sense. Okay, number 9. Looks like kind of the same thing. An airplane is flying on a bearing of 170. Okay, so stop and think about what that means. That's navigational. So 170 would look like this. At 460 miles an hour. So the magnitude is 460. So he's flying on a bearing of 170. You can get it, thank you. Flying on a bearing of 170 at a speed of 460 miles an hour. Your job is to find the components of the velocity vector, okay? So basically we want x and y. Now, just talked about the fact that x is going to be 460, that's the magnitude, that's a speed, right? Yep. Times the cosine of the angle in standard position. Do not use 170. 170 is not in standard position. You have a choice. You can find the blue angle, because that's in standard position, it's starting on the x-axis, or you can use the orange angle. It doesn't matter. Use whichever one you're most comfortable with. The orange one's going to be smaller, so I think I'll use that. How big will the orange angle be? Now remember, the whole big black one's 170, but that's 90. So this part would be, watch it, negative 80. It's going down, guys. It's going down. So that angle in standard position is negative 80. So 460 cosine negative 80, and y is going to be 460 sine negative 80. So I just type it in on my calculator. 460 cosine negative 80. So 79.87. Oh, 888, I guess. My rounding's all over the place, sorry. And then 460 sine negative 80, negative 453.01. Two things. Just to prove to you that you could have used the blue angle. How big would the blue angle be? Well, isn't the blue angle everything but 80? So what is that? 280? So type in 460 cosine 280, and you get exactly the same thing we got. So you can use the orange angle, you can use the blue angle, you can use any angle that's in standard position. All right, so that's the first thing I want to point out. Second thing is, look at the components of this velocity vector. This plane is flying, that's positive, so he's going east that far and south that far. Does that jive with the picture? It absolutely does. X is going to be positive, Y is going to be negative, and that's exactly how it came out when I used my angle in standard position. All right, what's next? All right, so leave San Francisco, flying a Boeing due east. There's a 65-mile-an-hour wind with a bearing of 60 degrees. All right, so here's the plan. Here's the deal. This guy, this airplane pilot, wants to fly due east, but there's a wind blowing out there. So she is not going to set her plane due east because the wind is going to push her off course. Your job is to figure out, okay, what direction should she fly in so that when the wind pushes her off course, she will end up flying due east. Okay, so you understand what's happening? We need her to end up flying due east when the wind pushes her. We want her final course to be due east, and her final course is going to be the sum of her initial course and the wind. I'm going to put due east here so we remember. Right? If we add her course and the wind together, we need to end up going due east. That's what the problem says. So what are the components of the wind? That's the easy one. What are the components of the wind? The X component of the wind is, I need to figure that out. Because all I know about the wind is its bearing is 60 degrees. So its speed is 65. So that's going to be 65 cosine something and 65 sine something. Would everybody agree with that? Magnitude, R cosine, R sine, X and Y. I need the angle to be in standard position though. So the biggest mistake that's made, and these problems that can be so complicated, but the mistakes are always so simple. You must use an angle in standard position. So that is not in standard position, but this is. So what angle should I be using for the wind? 30 degrees. So here are the components of the wind. This is the X and Y for the wind. Now, what about her initial course? What's the X and Y for the initial course? Well, I don't know the angle. That's what I'm trying to figure out. But I do know that her speed is 450. So her initial course is 450 cosine something and 450 sine something. To get her final course, I am going to add my X's and add my Y's. That's how I do it, okay? So what are my X's? My X's are going to be 450 cosine theta plus 65 cosine 30. So that is my final course. That's my resulting X. My resulting Y is 450 sine theta plus 65 sine 30. Now here's where you really have to have your thinking cap on. Because right now, because of that theta sticking in there, I can't figure this out, okay? That's her final course. That right there is going to be the answer to the question once I figure some things out. So I need you to go back to the original statement, which was she has to end up flying due east. You guys, if she has to end up flying due east, I have to end up flying due east. Then doesn't the Y, think of that vector right there, think of his components, his X and his Y, doesn't his Y have to be 0? If you are flying due east, then your Y is 0. So 450 sine theta plus 65 sine 30 has to add up to 0. So now I'm going to solve that equation, okay? We're going to solve that equation. So here we go. 450 sine theta equals negative 65 sine 30. So sine theta equals negative 65 sine 30 over 450. Now, because that's sine theta, what am I going to have to do? Because that's sine theta, what am I going to have to do to get theta? Well, I'm going to have to second sine. And that's going to give me my theta. Okie dokie. So second sine, negative 65 sine 30, close parentheses, divided by 450. The theta that I got when I solve that is negative 4.14 degrees. This is her final course, you guys, due east. We already know that's 0. That's how we set all this up and solve this. I need to find x. That's going to tell me her speed. That's going to tell me how fast she's going. Okay? So here we go. This is easy. This is easy. How do I find her x? Right here. This is her x. So what am I going to do? I'm going to figure that out, putting in negative 4.14 right there. So 450 cosine, I'll just do second answer since it's right there, close parentheses, plus 65 sine 30, cosine 30, 65 cosine 30, there we go. And what's her speed? What'd you come up with? I hope you came up with 505.11. So her x coordinate is 505.11. And her angle is negative 4.14. Okay? Well, I think that's, well, let's do one more. We'll do one more. We'll do number 11. We want to find a vector with a magnitude of 8 in the same direction as this vector. Okay, well, this is easy. This is a good one to end on because it's super simple. So let's go back to the beginning. What is the magnitude of that vector? What is the magnitude of vector v? Well, I hope you don't have to do this, but whoa. Negative 1, 3. I hope 3, negative 1. Oh man, it's time to quit, huh? 3, negative 1. So it looks like this, okay? Yeah, 3, negative 1. So the vector looks like this. I want to know how long that is. So it's going over 3 and down 1. So isn't its magnitude going to be root 10? 3 squared plus 1 squared, the Pythagorean theorem. Okay, the magnitude of the given vector is root 10. I need the magnitude of the vector to be 8. So here's what I want you to do. I want you to back up and make it a unit vector, okay? So we make it a unit vector by dividing everything by root 10. So the coordinates of the unit vector are 3 over root 10, negative 1 over root 10. Now its length is 1. Well, think about it for a second. If I had a vector whose length is 1, and I want its length to be 8, can I just times it by 8? So now I'm going to take these two coordinates. This vector has a length of 1, and I'm going to times it by 8. So the vector whose magnitude is 8 will be 24 over root 10 and negative 8 over root 10. So you can make a vector whatever length you want, stretch it, shrink it, however you want, by simply multiplying and dividing. And the way I always do it is the way I just did it. I turn whatever vector it is into a unit vector and then multiply it by whatever length I want. So if I wanted its length to be a half, I would turn it into a unit vector and then multiply it by a half. Okay, that's a lot. Thank you for listening. We will finish this section next time. Hope you're having a great day.